Yeah, hello everyone. Thank you for coming. And today we welcome Professor Yilun from Harvard University Computer Science Department to give us a talk about generative AI in the real world. And Dr. Du, Professor Du got his PhD degree from MIT, and he worked for DeepMind for a year, and now he will be joining Harvard's Computer Science Department in 2025 fall semester. Let's welcome Dr. Du for his talk on generative AI in real-world applications. Thank you.
Yeah. Anyway, yeah, thanks so much for the introduction. And I'm sorry I can't come in person. But yeah, if anyone wants to chat more, I'm in the Cambridge area for quite a while, so I'd love to chat. But yeah, overall, this talk will be talking a bit about this idea of how we can use generative AI to really get us intelligent physical agents. So overall, my research goal has been driven towards this goal of trying to get these like intelligent physical AI agents in the physical world. So if we look at current systems, they're only able to do really simple tasks. So like current robotic systems can maybe put one mug on a rack, or maybe the model can take one object and place another object on the other one. But what we really want is we want like intelligent autonomous robots that can do all types of behaviors that we have never imagined in open terrains. So what we really want is we want to construct robotic systems that can really robustly generalize to unseen distributions of tasks, environments, and other agents. But I guess one central question is, how do we do this? So typically when we think about machine learning, we think about this concept of a training distribution, and then we think about having a test distribution that matches the training distribution. So how can we build a system that, given a bunch of experiences of a certain set of tasks, can now generalize to new tasks that you've never seen before? So in this talk, I'll outline a general approach towards this problem of really trying to generalize outside the training distribution, and then I'll talk about some key components and results. So the general approach I'll talk about is this idea that we should really learn generative models of the world, and we should in particular learn probabilistic generative models. And I'll talk about how by learning probabilistic generative models of the world, we could actually use these to really plan adaptively at test times with search, and how we can actually build them compositionally out of individual components so that the world models can generalize to areas we don't have any training data in. So first, let me talk a bit about how generative models really allow us to plan and predict and plan adaptively at test time through search. So let's consider a task. So I'm a robotic agent. I'm in this house, and my overall task is climb up the stairs. Now, if I have a deterministic neural network, that neural network will take in the image, the task, climb up the stairs, and output a turned action trajectory to go up the stairs. And this is really great when your training distribution and test distribution matches. But what ends up happening oftentimes is in houses, people come or there are new obstacles, and oftentimes changes in the environment makes your predicted actions invalid. So what do we do in this setting? Well, one idea is instead of learning a neural network that explicitly regresses the action we want to take, we could instead have a neural network that encodes a preference over every single action. The idea here is now we have a neural network that takes in the image observation, the task, climb up the stairs, and it takes in that action trajectory. And then it outputs a single energy prediction. So that for every single action trajectory you pass in, you get a different predicted energy value. And this energy value represents the negative utility of the possible action. And now if you have this type of energy function, then you can infer the action to execute by optimizing the energy function. And this kind of corresponds to, and this energy function essentially corresponds to a probability value from the probabilistic generative model. So generative model takes in an action trajectory, an image, and gives you a likelihood. But the nice thing about formulating prediction is simply finding an action that minimizes this energy is that now you can do search at test time. So if I have a new constraint, for instance, I want to preserve my battery life, or I want to avoid going forward too quickly to preserve safety, I can construct a new energy function for this type of constraint. And I can take the original energy function and add this new energy function to get an overall energy function over action trajectories. Now, once I have that energy function, I can infer the action to execute by simply optimizing or searching for the action that minimizes energy. So one idea is by learning probabilistic generative models over the tasks you want to do, now you can go from explicit prediction to using search optimization to find new actions that can generalize to new settings by simply adding new constraints. So So that's the first idea of why probabilistic generative models might help us generalize. And the second idea is this idea that we can really build these generative models in a very compositional manner so that we don't necessarily even need data to be able to construct a generative model that has the properties you want. So we've all seen recently how large language models are really powerful. So if you ask a language model how to construct AI, it can give you these step-by-step instructions on how to do it. So one question is, do you even really need this compositional structure? Can generative models just automatically work as long as we just get enough data? Well, it turns out that at the current moment, still multimodal language models are not that good. So if you try to give a model an image of a scene and a text, is a blue cup below a red bowl, it instead answers incorrectly. And this example is around a year or two old, but still, if you take these the latest brand of multimodal language models, they still are really not that robust. And I think this has to do really with the distributions we really care about in the real world versus in natural language. So natural language is maybe a bit more simple than the real world in the sense that natural language was invented by people. It's very low dimensional, relatively speaking, because it's a very compact representation of the world that we use to communicate with others. In a sense, the language is very naturally compositional. So we see most combinations of words that we want to operate over. So in that sense, the training distribution in natural language is pretty similar to that of the real world distribution. But if we take the data that we see on an embodied agent or robot, the settings, the scenarios, the images, the goals that we want the system to operate over is much larger than the narrow amount of training data you've seen for solving a particular task. So overall, compared to the pixels of an image or many other continuous distributions, natural language is much simpler and naturally compositional so that we do not need as much of this generalization outside the data we've seen before. And what I'll talk about in this talk is this idea that we can still get generative models that can generalize outside this narrow training distribution if we make some assumptions on the modeling problem. And the idea I'll talk about a lot is this idea that, let's say we have this distribution of data. Instead of directly learning a generative model to model this entire distribution, we can choose to factorize the distribution. So we can learn one model for one axis of the distribution, and we can learn a separate model for the second axis of the distribution. And now, if we learn these factors for these two axes, the product of these distributions is able to generalize outside this diagonal you've seen before. Now, of course, for most tasks we care about, there's not going to be this natural axis factorization of the data distribution. But you can just, but the overall idea is if I have a set of variables, I don't learn a model over just independent, I don't learn a model over every single set of variables, but I learn a model over subsets of the variables. And then so long as this input variable X is in distribution for each of these subsets of variables, the overall model will be able to successfully operate. And of course, these factors make some independent assumptions about the data, but the important thing is they make these assumptions, but now they're able to generalize the areas where the data, where you don't necessarily have data. And now there's a question where right now it's very popular to just think about scaling up the data. We should just gather all the possible data of a physical robot, or we should gather all the data for whatever domain we care about. And if we look at the history of generative models, we have seen a pretty impressive amount of scaling. So when we look at images from 2015, where we have these very pixelated beds, to these images of objects in 2018, to very free-form text-to-image generation by 2022, it does seem like generative models have solely based off scale gotten much better. But it turns out that a lot of the changes, I guess one question that this raises is, should we just gather as much data as possible? Should we just gather data for whatever generative model setting we care about? But it turns out that actually a lot of these advances in image modeling that we've seen over the years is not due to just simply increasing the scale of the generative model, but rather due to a lot of different tricks that people have added to make these generative models work better. And in particular, from 2018 to 2022, we added this idea of class conditioning or text conditioning. So instead of just conditioning on the class identity of the image we wanted, or like in 2015, it was just, let's model the unconditional distribution of P of X. In 2018, it's let's model the distribution of images given a class identity. In 2022, it's now, let's model the distribution of images given a very detailed text description. And these three things are very different because the amount of uncertainty you have to model is much less later on. So if you just want to model the entire natural image manifold, there's a lot of uncertainty over what exactly is a good image. If you model the distribution of images given a class identity, there's much less uncertainty. And now if I give you a very detailed text caption, there's almost no uncertainty. And at the same time, we've also changed what we use to generate our samples. So in 2015, we learn a distribution and we sample from that distribution. In 2018, we learn from the distribution and then we sample from a much more truncated distribution. In 2022, we sample from this modified distribution that really tries to emphasize images that are maximally aligned with your text generation prompt. So one thing we can do is we can take this model from 2022 and we can simply try to remove some of these tricks. So let's say that instead of sampling from the modified distribution to generate images, let's just sample from the original distribution learned by the model. So if we sample from the original probability distribution learned by the model, it turns out the images no longer satisfy the prompts you want. So astronaut riding a horse no longer has an actual astronaut riding a horse. And in the same sense, if you remove the text conditioning, so if you just sample from the probability distribution P of X learned by the model, the samples look even worse. So a lot of the advances we've seen in image modeling or just generally continuous generative modeling aren't really due to improvements in just scaling the data or much larger models, but it's actually due to a lot of very careful engineering tricks. So overall, at the current point, these deep generative models cannot really fit arbitrarily high-dimensional distributions, but rather ones that are relatively simple. And you can make these distributions relatively simple by either conditioning on a lot of context or by considering domains with very low intrinsic dimensionality. And one way to think to consider all of the things about compositional generative modeling I talked about a bit earlier is that it gives you a way to really model very complex distributions using very simple ones. Okay, great. So that was a brief overview about the overall idea of this talk, about using world models to really allow us to generalize to new settings. So now I'll talk a bit more about these key components and details in more depth. So this talk will be structured in 4 parts. So first, I'll talk a bit about this idea of energy-based models. And then I'll talk about how these energy-based models can allow us to compose different generative models together. And then I'll talk about 2 applications of these models. So first, to planning, allowing us to solve new long horizon tasks that we haven't seen before. And then how it can really be combined with a large multimodal models for more intelligent decision making. So first, let me talk a bit about energy-based models. So let me first give a little bit of a background. If we consider an energy function, for example, a red truck energy function, this energy function takes in an image of a green truck and it outputs high energy. And an energy-based model for red trucks, when given a red truck, will assign it low energy. And essentially, the energy function parameterizes this probability landscape over the space of all cars, so that images of, or not even all cars, but all images, so that images that have red cars have low energy and images that have green cars have high energy. And once you have this energy function can implicitly encode a lot of different things. On one hand, it can encode some type of utility, similar to the example I talked about at the beginning of the talk. The energy function can also encode whether you're inside a set or not. And finally, this energy function can encode any type of probability distribution you care about. Now, once you have this energy function, the question is, how do you actually effectively sample from this distribution? So naively trying to sample from this energy function is hard, because if you have a very high dimensional space, there are exponential number of points. So it's very hard to find one that actually has low energy. So one idea to really more effectively sample from distribution is to use the neural network to help guide your sampling. So one idea is you can use the gradient in the energy function to help you find your sample. So given a noisy sample, you can use a gradient descent step respect to energy to help you find a slightly better sample. But one issue with just using gradient descent is that you actually don't sample from the entire probability distribution of the model. So in 2019, we proposed to use Langevin dynamics as one way to really scalably sample from these high dimensional energy functions. And it ends up looking something like this. So you have this landscape here, and then the gradient descent step attracts you to one mode of the distribution, and the added Gaussian noise helps propel you from one mode to the other probability mode. And in the image space, it looks something pretty similar to people. It looks quite similar to a diffusion model. And I'll talk a bit about the connections of energy-based models and diffusion models in a little bit. And one way to think about this generation procedure of Linderman dynamics is that it really trades off the ability to generalize, the ability to do new things that you haven't seen before, with generation speed. So if you look at something like a GAN or a VAE, the generation is almost instantaneous. You're taking the input and generates the output. But with this more energy-based formulation, the generation is much slower because it's a stochastic optimization process, but allows you to change the generation problem by just simply changing the energy function you use for sampling. So let me just give a brief overview on how you can actually train energy-based models. So if I have a data distribution P of x, I really want to learn an energy function that represents a log probability, log P of x, so that the learned distribution P theta of x is proportional to e to the negative energy of x. And it turns out that we can compute the gradient of log probability. So if we take the gradient of log P theta, it ends up being a decrease in the energy of ground truth data minus decreasing the size of the partition function, or the energy that you assign to all other data points. So if you distribute the gradients a bit, training an energy function essentially corresponds to this contrastive objective, where you draw samples from the ground truth data, and you try to decrease the energy of those samples. And then you draw samples from the underlying energy-based model, or the energy function, using this Langevin procedure, and you increase the energy of those samples. And in practice, it's hard to actually draw samples from this learned distribution. So people have been training these energy-based models for several decades. But in 2019, we illustrated how by using Langevin dynamics in the image space, we can really draw samples from this distribution and train these energy functions much more robustly. So here's the illustration of how energy-based training works. So at the beginning, you have this flat energy landscape where both images of red trucks as well as Gaussian noise all have the same energy. And then you have this contrasted procedure where you decrease the energy of red trucks while increasing the energy of the sample point. And now you have a much more evolved energy landscape where if you sample from it again, now you get an image that looks a bit more like a red truck. So it looks a bit like this noisy red truck. And you repeat this procedure where you decrease the energy of red trucks while increasing the energy of the noisy red truck. And after repeating this a lot of times, eventually you decrease the energy of red trucks and you increase the energy of red trucks. So at that point, your training procedure has converged, and you have an energy landscape that has low energy at all images of red trucks. And now you can actually also view diffusion models as energy-based models, which allows you to actually use a lot of these operations more broadly. And roughly, so this was this generation procedure we proposed in early 2019. So we have this kind of noising process, and then from the noise, you gradually get images of different objects. So based off our work, or like building on top of our work, there's subsequent follow-up work on score-based models, which adopted our this Langevin sampling procedure on images, but where instead of explicitly learning the energy function using the objective I talked about earlier, you actually approximate the gradient of the energy function with this denoising network epsilon that you can learn from denoising. And then there's some math that shows from a couple of decades ago that shows that the denoising objective approximates learning this gradient of this energy function. And you can view diffusion models as a type of score-based model where there's a bit more of this contraction of the sampling, contraction of the input over sampling. But you can see that the overall sampling procedure ends up looking exactly the same as the Langevin sampling procedure that we proposed earlier. And then you essentially can just interpret diffusion models, energy-based models, where you just interpret the denoising function as a gradient of the energy function. And you can also change the parameterization of the diffusion model so that instead of parameterizing it using this denoising function, you can parameterize it with the energy function, which we show in this paper. So in my work, I've illustrated how a lot of these energy-based models can be used across a variety of different domains, such as images, robot plans, text, proteins, videos, and 3D shapes. But I'll talk about, and I guess in the talk, I'll mostly talk about the applications in robotics, but these can be used in a lot of other domains. So now, given this introduction on energy-based models, let me talk a bit about why this idea of using energy-based models can be very powerful, allowing us to compose models together and solve new tasks. So let me start with an example. So if I want a neural network to generate trajectories, let's say I want to have a neural network generate trajectories that reach a particular goal, that have a particular gate that avoids obstacles. The normal way to do this is by simply adding loss functions. So if I have 3 loss functions for these 3 objectives, I can take a neural network, I can train it to optimize these 3 loss functions, and I can get a neural network that has all the properties I want. The issue with neural network training is that you can't really do this procedure here if you just want to do this composition at test time. So if I have one neural network that generates trajectories that reach a goal, a separate neural network that generates trajectories that have a particular gate, and a third neural network that generates trajectories that avoids obstacles, I can't just add the predictions of the neural network together to get a neural network that satisfies all 3 of these properties. In a sense, this training process compiles a neural network that solves each task, and there isn't really a way to combine these neural networks together. And you can view this idea of energy-based models as an intermediate compilation of training that allows you to compose multiple different loss functions together. The idea is if you have a loss function for reaching goals and another one for having trajectories of a particular gate and a third one for having trajectories avoid obstacles, you can use these 3 loss functions to learn 3 separate energy-based models, where each energy-based model encodes a set of trajectories that satisfies a specific property, either reaching the goal, having a particular gate, or avoiding obstacles. Once you have these 3 energy functions, you can now add the 3 energy landscapes together. And this composed energy landscape will exactly have be low energy on the trajectories that have all 3 of these properties. And now by running a small number of optimization steps, now you can get a prediction that has all 3 of these properties. So essentially, energy-based models are intermediate loss compilation that really allows us to have composition through addition at prediction time. So at the expense of making inference slower, this intermediate abstraction allows you to compose things much more flexibly at test time, even when you don't have data for it. Whereas even if we look at the first example I talked about, where you just combine the loss functions, you have to have data with all 3 of these properties to train the neural network. Okay, cool. But now let's go back to this previous setting that I talked about. So let's say I have an energy function for red trucks. So if I directly minimize that energy, I get an image of a red truck. The nice thing I can do with energy functions is now I can have multiple different energy functions. Energy function for red trucks, another energy function for the desert. And now at test time, I can simply compose these energy functions together. And by composing these energy functions together, now I can get an image of a red truck in a desert. And in practice, when we combine these energy functions together, they have a magnitude, but each of these magnitudes may be very different. So you do have to control the influence of each energy function by scaling the relative magnitude of the energy function. So now let me show. So it turns out that when you combine these energy functions, there's a different algebra in which you can combine them depending on what energy function represents. So if an energy function represents utility, then adding 2 energy functions corresponds to utility addition. In contrast, if an energy function corresponds to set membership, whether you're inside a set or not, then adding the 2 energy functions corresponds to determining the points that are inside either set. And if you have energy functions that represent probability distributions, adding the 2 energy functions together represents a product of the 2 distributions. And there are a lot more operations also that you can do with energy functions that I'll go into more detail next. So first, let's look at combining energy functions over sets. So imagine I have an energy function that has low energy at all points in this blue set. And I have a second energy function that has low energy at all points in the orange set. Now, if I directly add the 2 energy functions together, I get a new energy function that has low energy at all points in this intersection of these 2 sets. In contrast, if I have energy function for the blue set and energy function for the orange set, and I take the soft min of these 2 energy functions, now I have an energy function that has low energy in all points in either the first set or the second set. And finally, if I have an energy function for the first set and an energy function for the second set, by taking the second energy function and subtracting the first one, now I get a new energy function that has exactly low energy in the points that are in one set, but not in the other one. So by simply adding multiple energy functions together, I can now implement logical operators on top of these energy functions. And it turns out that with suitable thresholding, you can further nest these energy operations together. So now let me show some empirical results showing this. So we train an energy function for generating images of a green cylinder behind a yellow cube. And we trained another energy function for generating images of a gray cylinder below a brown cube. And now, by using the earlier set operations, we can generate images of a gray cylinder behind a yellow cube, while also not having a gray cylinder below a brown cube, which are these images. But I can do more complicated nested generations also. So I can, by combining multiple of these operations, I can generate images of a gray cylinder behind a yellow cube and a gray cylinder below a brown cube, which are these two images, or a gray cube behind a brown cube, and a gray cube right of a blue sphere, which are these two images. So you can nest these operations to do much more complex sets. And then more broadly, you can also use these energy operations to just implement different combinations of probability distributions. So you can, by adding the two energy functions, you can implement products of two distributions. By doing some type of softmax over the two probability distributions, you can also implement the mixture of the two distributions. And by simply subtracting one energy function over another, you can also implement inversion of one distribution with respect to the other. So P1 of x divided by P2 of x. And this suite of probability manipulation operations has a lot of different use cases you can use. So what you can do is you can use this, for instance, for much more compositional text-to-image generation. So if you have a really complex text prompt, you can decompose it as three probability distributions. One model that models a couch right next to windows, one that models a table in front of the couch, and the third that models a vase of flowers on top of the table. So by taking the product of these three distributions, you can essentially generate images that has all three of these factors compared to a single model that is unable to follow all the instructions. You can also use the product of probability distributions to adapt the style of a generation. So if you have a video model that has a particular image generation style, then by multiplying it with another distribution or composing it with another distribution, you can change the style to other styles. You can also take these probability distributions and really apply them to different parts of an image. So by doing this, you can take a text-to-image model and you can really controllably generate objects at different locations. So you can controllably say, I want the Starship Enterprise here, I want Mars here, I want a robot here, I want the sun here. And by just composing these distributions over each part of the image, now I can generate a scene with all these objects. And finally, you can also take probability distributions in a more robotic setting, where each probability distribution encodes a constraint. So maybe one constraint is I want the object inside this box. I want to make sure that robot manipulator grasps the object. I want to make sure that the robot manipulator moves my object to the other object. I want to make sure it doesn't collide with other objects. So we can formulate manipulation of a set of objects as simply composing a set of these probability constraints. And then we can just add the corresponding energy functions and optimize them to solve these new tasks. So so this type of composition can allow you to adapt and use generative models for all types of flexible downstream of tasks. And then in practice, there's some small technical details with compositional sampling. So as you compose these energy functions, especially when these are very high dimensional, the more functions you compose, the more high dimensional or complex the energy landscape becomes, and then the harder it is to sample from them. So it turns out that you can use diffusion models to make this a bit easier. And you can essentially interpret diffusion models as learning a sequence of T energy-based models. The first one where it's Gaussian noise, and the last one, which is your target distribution. And essentially sampling from these T distributions defined by the diffusion model corresponds to some type of annealed importance sampling, where you run some Langevin dynamics on one distribution, and you contract it to move on to the next distribution. So roughly what you can do is to sample from a product distribution or the product of two probability distributions, you can just add the two denoising functions, and then you can just use Langevin dynamics with a contraction term on it. And then it turns out that this isn't exactly correct. It turns out that you need a particular score function for sampling from the product distributions, which is not exactly the addition of the two distributions. But you can solve this by just interpreting the diffusion model as simply defining a set of T separate separate EBM distributions, starting from Gaussian noise to the target product distribution. And the idea is you don't use the normal diffusion transition kernel where you use the score function and integrate it. Instead, you just use the annealed MCMC. So you draw samples from the first Gaussian noise distribution and run a couple of steps of MCMC, which is just the Langevin sampling procedure earlier. And now once you run a couple of samples using this composed score function, so the score function, the denoising function for the first distribution and the second distribution sum together, you run a couple of steps of MCMC, and then you transition the sample to the next sample and repeat it. And this sampling procedure can be done very similarly to normal diffusion sampling, but where you just simply have several multiple reverse sampling steps at each noise level. And the idea is each step is used to sample from the energy landscape as opposed to explicitly transitioning between one landscape to the other one. And this is what it roughly looks like when you do this compositional sampling with diffusion models. Let's say I want to sample from this final target distribution here. Well, then the diffusion sampling procedure gets you this more like spherical distribution at the beginning, then this more ring-like distribution, and then finally the target distribution. The final thing that I'll talk about is this idea that you want to really discover these composable components. So so far, I've talked a bit about how like we have these composable energy landscapes, and then we can compose them to do all these flexible tasks. But one question is, let's say I just gave you this distribution here, like some distribution along this diagonal. How do I actually infer these components that I can use to compose? Like, how do we discover these independent components of distribution? So I would just present a really simple algorithm, and I think there's a lot more work that can be done in this area. One really simple algorithm is simply we just represent the distribution we want to model, P of x, as a product of just independent factors. So we just represent P of x as this product of factors. And then this gives us a pretty simple objective. So let's consider modeling the distribution of a reconstruction of the image. So I condition my model on a particular image, and I want to learn a probability distribution over the reconstruction of that image. And the idea, and we can translate this to modeling this in a factorized form by simply modeling this distribution P theta of x given image as a product of P thetas over each axis of the distribution. So we have n separate axes. So this corresponds to saying that given the original image, I want to infer a set of latents so that when we sum up all these energy functions together and optimize it, the original reconstructed image is the one that has the lowest energy or highest likelihood. So this corresponds to the energy objective that I said earlier, where like we want it to be the case that when we optimize the sum of the energy functions, they have you get the original image. And then with this objective here, we can enforce that these energy functions capture different parts of the scene or like different objects in the scene through information bottlenecks. So we can simply restrict the size of the latent dimension, and that enforces that the energy functions captures each individual object in the scene. So let me show a couple examples of how this procedure allows us to really get multiple or like discover multiple different energy functions that represent parts of the image. So here I have this original input image of these four objects. And what we find is we infer these four energy functions where this shows the optimization procedure, but the energy functions actually get different parts of objects in the scene. And in contrast, if you have this image here, the separate energy functions corresponds to parts of the image. So you have the facial expression, the skin, the background, and then the hair color. So essentially, this objective here allows you to discover these independent factors on the distribution. And now when you sum up the energy functions where you take the product of the probability distributions, sampling from that allows you to reconstruct the original image or get you a face. And again, the main benefit of really discovering these individual composable energy landscapes is that now they allow you to generalize. So here, let's say I have one data set consisting of spheres and cubes, and I have a separate data set consisting of boots and trucks. Now I can take two components that we've discovered. Let's say here they represent this this cube and sphere. And then I take two other energy functions discovered in the second data set. So these are two completely separate models. And if I simply compose these two energy landscapes together, now I can get a scene that has a mix of objects in both the first data set and the second data set, even though there is no real world image consisting of objects in both data sets. So by inferring the right individual components, you can actually generate scenes that are very different than what you've seen before. Okay, great. So the first two parts, I just introduced some energy-based models, and I introduced how we can really compose them. So now I'll talk a lot more about how this idea can be more applied to robotics as well as to multimodal models. So first, let me talk a bit about robotics. So let's look at what people can do. So let's say I want to make a BLT sandwich. Well, we can do a very large number of different tasks, ranging from finding a tomato, cutting the lettuce, and so forth, to really make this overall BLT sandwich. And we really want to construct robotic agents that can be physically intelligent and solve the wide range of tasks that people can. But what the issue is, well, if I just directly try to learn a generative model to do this, this is really challenging because I would need to show demonstrations to the robot of me cutting lettuce in every single kitchen out there. I need to show demonstrations of cutting tomatoes everywhere, or putting bacon or like toasting bacon or so forth. So there's so many different tasks you want to do in so many different environments. So it's really hard to get the space of demonstrations to cover the entire space you would want your robot to execute over. So one idea is that we can decompose the demonstration into two models. So one model that models the goals of the agent, and the second probability distribution that models the dynamics of the agent. And now if we can model this distribution as the product of these two models, then this allows you to essentially solve a lot of tasks that you might not have data for. And the idea is that you can take the dynamics, the knowledge of the dynamics of the world that you've learned from the first model and stitch it together with the goals of each task that you've learned, allowing you to like take the take an environment that you've learned task 1 in and solve task 5 in it, because you can just use your knowledge of the dynamics in task environment 1 to solve the goal of task 5. So if we look back at this energy diagram of composing energy functions, this corresponds to taking a trajectory level energy function on top, and then having an energy function for costs or the goals of the agent, whether it's a goal, whether it's a value function, or it's test time constraints, and simply combining these two together. And then once you combine these two energy functions together into this one, then you run some type of optimization on this. And this allows you to implement planning and reinforcement learning through test time search on these composed distributions. So let me show a couple examples of this. So first, let's say I have energy function for trajectories here, and I have a separate energy function for the rewards of the agent. So this is energy function 2. Now by adding these two energy functions together, now we have an energy function for optimizing RL policy. And the nice thing about this type of energy function is I can learn this energy function for dynamics on maybe one environment or like one task. And now by simply combining it with an energy function for rewards for a multitude of other tasks, now I can take this model and use it to solve all types of different tasks. And what we find is that this approach, where we simply combine this trajectory level model with a reward function, it turns out that this approach actually performs very, very comparably to the state-of-the-art offline reinforcement learning techniques, even though we actually don't even do explicit reinforcement learning here. We just simply take the model and we just plan on it. So we just take the model and the reward function and compose it. So this model here that performs as well as these other approaches can be used in all types of, can be used to solve multiple different tasks and not just a single one. Another thing that you can do by composing these energy functions is to do some type of planning. So let's say I have an energy function over the dynamics of a trajectory here on top. I can have a separate energy function that just specifies a particular start state as 0 and a particular go state g. And now by composing these two energy functions together, I now have an energy function that has low energy exactly when the start state is S0, the go state is G, and so that every single intermediate transition in the trajectory satisfies the dynamics we want to that we've specified. So this allows us through composition to construct a zero-shot goal-seeking policy. And here we have a trajectory level model that's been trained on all types of random trajectory transitions in this environment. And now by simply specifying a start state and go state and running optimization on it, we now can get trajectories that go from that particular start state to go state. And what we find is that this type of planning allows us to substantially outperform baselines while requiring no task retraining. So this model requires no training at all and is directly able to zero-shot solve all these tasks. And the final thing you can do with this energy function composition is you can take an energy function over trajectories, and you can compose it with a separate energy function that specifies costs at each state. So costs at state 0, state 1, state 2, state 3, and state 4. And these costs can be hand constructed or learned. And then by optimizing this, we can use this to implement some type of trajectory optimization, or like implement like optimization with respect to any set of costs. So here we have an energy function that's been trained to stack blocks together. And now by constructing a set of energy functions, one that specifies I want the gray cube on top of the purple one that specifies the purple one on top of the red, and the third that specifies the red on top of the blue. By simply zero-shot optimizing this, now we can get a stack of now we can get a policy that can stack blocks on top of each other. And it turns out that this type of planning you can also do when you don't actually have the exact state of the world. So we can imagine that we only have an image observation. And then even if we only have the image observation, we can still do optimization over the future states and actions we want to execute. Even if we don't know where we are right now, because this model is just is a learned neural network that's defined over image observations. So one nice thing this allows us to do is that it allows us to really do like a pretty autonomous visual motor policy control. So by here, we are just we're just planning over the sequence of the next set of actions. And we can see that this policy is able to autonomously reorientate the mug given only very few 50 demos. And then that this type of model can also be used to solve all these tasks here, where you can also use this policy to like autonomously spread the sauce here. And then you can also use this type of trajectory level energy function parameterization to really learn video space planners. So here you have an energy function for your trajectory, and then your goal function or cost function that you optimize or respect specifies a natural language instruction of the task you want to solve. And now by composing both of these two models together, you can use this model to really plan across a wide range of different environments, because you can use a space of images as a unified abstraction of different trajectory state spaces. So you can imagine that if I want to generate a plan of a robot picking up an object and stacking it and placing the object next to the other object, well, I can just represent a plan for solving this by synthesizing a sequence of images representing that plan. And we can also use the model to synthesize a sequence of plans to wipe this board over or to pick up a silverware utensil. And then once you have these plans, these visual plans, you can then use a separate inverse dynamics model to infer the actions to execute in the environment. And one nice thing about formulating planning in the video space is that it also allows us to learn policies directly from videos on the internet. So there are a lot of videos of people opening doors. And you can imagine that once you have a model that learns to open doors based off this, then it can actually use the knowledge that's learned from the internet and apply it to planning in the robotic domain. And one thing to note is, I guess we were doing this around 2 years ago, and at the time, video models were maybe much poorer than they were now. But you can see that these video plans are actually highly realistic. So like this plan here, for example, you can actually see that it like is able to like reorientate the object fully. Great. So the previous section, I talked about how this compositionality can allow us to do planning. So finally, I'll talk about how this compositionality can be just more broadly used across different multimodal models for more intelligent decision making. So let's consider a very long horizon task, for example, making a cup of tea. So effective decision making to solve this task requires integrating a lot of different aspects of knowledge. So you need to have some type of like common sense knowledge about where to look for a tea kettle or the steps necessary to steep the tea. You need to have some visual knowledge of the world. So you need to know the identity and the intrinsic properties of objects and 3D geometry of the world. You need to have some physical knowledge. You need to know like the underlying masses, materials, and masses of objects. And you need to have some knowledge of control. So you need to know how to actually pick up an object or make contact with the object. So you can imagine that if you really want to get an agent that can solve these super long horizon tasks, that it's especially hard because we need to vary all of the different steps, like ranging from like the different steps necessary to make tea, the like different visual like arrangements of the world, the different types of physical knowledge, like the different physics of the objects, as well as like how to actually control objects. So to get demonstrations that cover this entire space is extra hard. And also getting a single demonstration is really challenging because now like a single demonstration could take you like 20 or 30 minutes to gather. So in this setting, one thing we can do is, again, we can use this idea of compositionality to really decompose and solve this task in a zero-shot manner, where we don't even need any long horizon demonstrations that actually show us how to solve this long horizon task. And the idea is we just simply use different existing foundation models to, as our sources of semantic knowledge, our visual knowledge, physical knowledge, and control knowledge. And by zero-shot composing these models together, now we can get a policy that can solve very long horizon tasks. So I'll talk about this in more detail next. But first, let me just introduce slightly more machinery on how we can compose different foundation models together using this idea of energy functions. And the idea is that you can really interpret any type of foundation model or pre-trained model as having an energy function just via the loss function that's been used to train it. So if I have a large language model, the likelihood loss or the likelihood of the language model on an input sequence corresponds to an energy function or loss, where if the likelihood loss on the input is low, that means that sample is highly likely under the large language model. Or similarly, I can interpret something like clip as defining an energy function via the language vision alignment loss. So if I have a language pair and an image pair that are aligned with each other, then the clip loss is low, and that means that it's in distribution for clip or matches the knowledge encoded by clip. So any type of foundation model via its loss function encodes the energy function. So how can we use this? So let me show an example of how we can use this interpretation of foundation models as energy functions to enable us to solve new tasks. So let's say I have a question, what is the cat doing? And I have the image of a cat right here. Now, a large language model cannot directly solve this task because a large language model cannot see the image of the cat. It can only generate a sequence of language instructions. In contrast, a clip model can also not solve this task because although it can understand the image here, it actually cannot parse the question. So neither model in isolation can solve this task. But one idea is that by composing two energy functions together, so if I take the clip energy function and I take the large language model, and I directly combine or sum up the energy functions, now I can get a model that can solve this task. So if I can find a language response so that it minimizes the clip energy function, so that the language response aligns well with the image, and so that the language response minimizes a large language model energy function, which means that it's a plausible completion given the question. Well, if I can ever get a response that satisfies both of these constraints, now I can solve this vision language task. I can solve this captioning tasks. And so essentially we can formulate solving this task is simply optimizing these two energy functions. And it turns out that one small issue with this is that if we want to actually optimize the sum of these two energy functions, it's slightly tricky because the space of language is discrete. So there isn't well-defined gradients. And also because like you might not necessarily have black box access to these models, so you cannot actually get the ground truth gradients. But one idea is you can still solve this optimization problem by using one generative model to help guide your optimization process. And the idea here is now we can use this large language model to actually guide our optimization. So we can say that optimizing for an answer that minimizes both of these energy functions is the same as simply drawing samples from the second energy function and finding ones that minimize the first one. So the idea here is we just simply take the large language model, we draw a lot of samples from it, and then we find ones that are aligned with clip, and then we repeat this procedure, we repeatedly refine it until we get an overall answer that minimizes both energy functions. And it looks somewhat like this. So initially you might have an answer, the cat is catching a mouse. By running some steps of optimization, you get a better answer, the cat is walking to a house. And finally, you get an answer of the cat is walking in a yard. So this sequential optimization procedure eventually allows you to solve this task. So one idea to view this is we can interpret foundation models as energy functions, and then you can use energy optimization as a zero-shot way to really combine information across models by treating each model as a constraint. So now let's look back at the task of the hypothetical task of making a cup of tea. So if we want to make a cup of tea, a language model provides you a lot of information in the sense that it tells you to look for a tea kettle, tells you to heat water or find the tea bag. So it can tell you these really high-level steps on how you can make a cup of tea. But it doesn't tell you the whole thing on how to actually solve this task because it actually doesn't tell you it doesn't actually tell you that detailed physical actions necessary to solve the task. And this language plan might not even be possible in the world. So if you have a large video model similar to the video space planner I talked about earlier, this model can tell you a lot of information about how you can pour tea. But again, this model doesn't tell you everything. So this model does not tell you the high-level steps necessary to solve a task, nor does it tell you how to actually control the robot to solve this task. And finally, if we have some type of goal condition policy, so some policy that takes in the current image, as well as imagined future that you want to reach, for instance, something generated by this video model here, well, this model has a lot of kinematics information. It can tell you how to actually pick up an object to reach that goal, but doesn't have any of this information that you want from the high-level models. But we can actually combine all three of these models together using the product of these probability distributions, or summing up the energy functions. And the idea here is that we can formulate successfully solving this task of making a cup of tea is finding a text plan, an image plan, and an action plan that's high likelihood across a large language model, meaning that it's a plausible text plan to solve this task. It's high likelihood was under the video model, so that given the text plan as well as the synthesized video plan, we can actually that it actually satisfies that, like, there is a physical world, or there is a visual imagination that allows you to solve the text plan, meaning that the text plan is grounded in the visual world, as well as getting an action plan, so that, like, given this sequence of video plans, the action model can envision a set of actions that could execute to match this image plan. So essentially, if we can optimize from this product of these three distributions, which corresponds to that iterative, which corresponds to optimizing some of these three energy functions, now we can get a plan that successfully solves this task. And it ends up looking something like this. So, so you have a large language model. In the large language model, essentially proposes maybe a set of actions that are possible for solving the task. And now the video model now the video model tries to synthesize video plans for each of these language tasks. And then it will be able to successfully synthesize video plans if the language model's generations are grounded in the environment, and it will not be successful if it's not. So it provides feedback to the language model, allowing the language model to extract a language plan that is plausible in the world. And then similarly, when you have a lot of video generations, you put all those video generations to this egocentric action model. The egocentric action model selects the one that seems the most promising, and it uses it to select the most promising video plan. So by just doing this, like, sequential optimization across both of these levels, now you get a set of language, video, and action plan that's consistent across all three of these models. And so you can view this like iterative inference time energy optimization as a planner to synthesize consistent plans across knowledge across all three of these levels. So here's an example of this. So let's say I have a goal, stack a red block on top of a cyan block and place a brown block to the right of the stack. Well, the language model might make a plan, place a cyan block in a brown box. And now the video model can give you some feedback and say, well, there is no cyan block in the scene, so I can make this video, but the likelihood is low. And you should just try making another language plan. So the language model might then make a plan such as place this white block in a cyan bowl. And now the video model can synthesize this plan where it's actually a feasible execution in the world. So in this way, the communication between the language and video model allows you to constrain the language model to make visually grounded plans. And you have some similar procedure between the visual model and the action model. And the overall composition of these three models allows you to implement the goal, stack a red block on top of the brown block, and place a yellow block to the left of the stack. And then a final small, this is the last part of the talk. The final small part of this is that in practice, if you just have a language model and video model, this ends up being a bit slow because the language model has to propose many plans before you have one that is optimized by the video model. And the video likelihood might be a very hard objective to optimize. So in general, you can make this composition between models a bit faster by simply making some of these models cross-modal. So instead of having a language model, you can now have a vision language model. So now the vision language model can take in the image as well as the language plan and output a set of visually grounded plans. And now the video model can synthesize each of these plans, and you can use the vision language model as a heuristic function to essentially choose which ones are most likely to optimize the video likelihood. So this is what it kind of looks like. So now you have a goal. Let's say put the fruits in the top drawer, and you have this corresponding image here. And now the vision language model will generate two possible instructions: either place the banana on the top drawer or open the top drawer. Now, given each of these instructions, now the video model will take the image as well as the text plan, and it will synthesize each of these videos. So here's place the banana on the top drawer, and here's open the top drawer. So you can see that the video model is able to imagine each of these settings. And once you have these video imaginations, instead of using the video likelihood to select the most promising plans, now you can take the video plan as well as the text go, and you can have the vision language model assess how much progress we're making. And if it's this plan here, because there's no top drawer, well, there's not much progress, so the vision language model estimates very low progress. And in contrast, this is making progress to the goal, and the vision language model estimates much more progress. So once you have this optimization procedure between the video model and the vision language model, where here we want to optimize for a set of images from the video model that satisfies this vision language model, now we can do some type of search on this to actually optimize this overall procedure. So if we have this goal, put the fruits in the top drawer in the starting image, the vision language model will expand it to these two possibilities I talked about earlier: open the top drawer or place the banana in the top drawer. You can just repeat this procedure where you continuously imagine in your imagine future text actions in your imagination space until you get an entire sequence of plans from opening the top drawer, placing the banana in the top drawer, placing the apple in the top drawer, and then finally closing the top drawer. So overall, what this enables us to do is it enables us to take a vision language model, a PaLM model, a video model, UniPy, and an action model, goal condition RT2, and it allows us to compose these three models in a zero-shot manner to solve an unseen long horizon task. So here we have the goal of put a fruit in the top drawer, and none of these three models have been trained on this task. But this composition allows us to actually successfully solve this task. Where here the model makes a mistake, and then you can replan until you can finally close the object and solve this task. And here's another example of this overall video plan where we have a goal, make a line. And now the video model, and here you can use the same planning procedure to make a detailed language plan of solving this task, and as well as this detailed video plan. So this is a purely imagined plan of actually moving objects so that you can make a line. And you can also convert this overall execution into a real manipulation policy of making a line. And what we find is that this type of compositional approach requires no it only requires a much less data. So you just need some vision language data, some paired video data, some action data. But this type of compositionality really allows us to solve these long horizon tasks much better than existing end-to-end approaches. So if we try to just use a large end-to-end VLA model, that performs very poorly. If we try to use a hierarchical VLM model plus a policy, also performs poorly, or a large video model also performs poorly. So this composition of these foundation models really allows us to solve much harder long horizon tasks. So overall, I've talked about this overall idea that if we really want to get AI that generalizes to new situations or settings where we don't have data for, then we should really learn generative models of the world. And then where these models are really allow us to do search at test time, and really where we can build them in a compositional manner for a zero-shot and generalization. Thanks everyone for listening, and I'm happy to take any questions.
Hi, Dr. Do great presentation. My name is Saber, and I'm research scientist at Harvard Ophthalmology AI Lab. I really enjoyed the notion of compositionality of energy model. I have a question about generalizability to the unseen tasks. So as you know, our application is more on surgery, and the data set we have are surgical videos. And so, because of the data privacy, we are not allowed, most institutions are not allowed to release their data sets publicly. So we don't have an internet scale data set, right? And more than that, we don't have language instructions customized for surgeries, to my knowledge, as of now. So given that, how can we generalize this foundational robots, for example, vision language models, vision language action models, to that customized application of surgery? And one step further is how to do so, to do it for microsurgery. And also the examples you showed us was for one robotic manipulators. How about collaborative robots? Let's say we have like two robotic arms doing, for example, some surgical tasks. Thank you.
Yeah, thanks so much for the question. So I think one thing you could do in the setting where you have these private data sets and is that you can imagine that you learn like in each institution's private data set, you learn like a task-specific policy, kind of like this action model I talked about at the end. And you could imagine that you could learn a video model or this vision language model on a lot of the like internet data. And then you can imagine that again, you learn you can learn a small model on your task-specific data to like kind of fine-tune the model on your task-specific setting. The idea is like by breaking up the problem into these compositional parts, well, you can take a vision language model or you can take a video model, you can directly like apply it on your task, and then have a smaller task-specific model that actually is trained on your specific task to like adapt to your particular robot. And now on the second question of how you can actually use this for collaborative robots. We have a paper actually called Compositional World Models, but one idea is the like tree search or like this like planning procedure I just talked about in the last 10 minutes of that talk. You can imagine that you could do this with multiple robots also. So you have like maybe you have the actions of robot 1 and robot 2 or robot 3, and then kind of combine these actions and use it to essentially imagine the future of that action. And so you can actually you can do some of this planning not with just one robot. You can also use it to do planning with multiple robots.
Thank you. And sorry for taking too long. I have another question. So how about the safety? So let's say the robot do some wrong surgery that can injure the patient. So how about to like prevent the robot from further doing the task and like undoing the task or replanning or something similar?
Yeah. Yeah, so I think one nice thing about so I guess another thing that I talked a lot about this is like this idea that you want to learn some model of the road, so or like plan on top of that model. So I think one nice thing about like instead of just learning a policy like a VLA model, like if you actually learn some type of dynamics model, you can actually simulate what would happen with each of your actions, right? And you can select the one that is most like you can select the one that seems the most safe. So if you can simulate what the future looks like for each action, you can use that to avoid anything that's potentially dangerous. And you can also imagine that if conditions change, you can replan very frequently using your old plan as an initial point, and that can allow you to adapt to any changes in the environment.
Yeah, I have a question. So it's also interesting about knowing about the energy optimization or something. So is there any limitation about using energy optimization techniques instead of using usual cost functions or something like that? I mean, is there any limitation?
Yeah, well, okay, so I think cost functions, right? So the nice thing about cost functions is they like like if you optimize a cost function, right? It's depending on how you define your cost function, you know that you satisfied your constraint or not. So with these energy functions, they're learned by neural networks. So as a result, like they're not 100% reliable. So sometimes like you will minimize the energy function, like the constraint the energy function is supposed to represent, and you don't get something that actually minimizes the constraint you care about. So in that sense, it's less safe than like having explicit constraints.
Question, can you involve
yes, can you involve in this combined model some real world physics simulation of the environment?
Yeah. So you could definitely actually combine some like so you can definitely combine this model with like with some type of real world physics simulation also. So I guess in this sense, this framework that I propose is just like this idea of combining these energy functions. So you could imagine that one of these energy functions is the actual real world physics simulation where you actually simulate the actions and then evaluate the actual like costs based off of your simulation states. And yeah, we're actually exploring a number of projects in this area, and I would be very interested in collaborating in an area like this. But yeah, I think you could definitely combine this with some type of real world simulation also.
How about giving a larger weight to the physics simulation than the
the learned energies.
Yeah, you could totally do that. Yeah, you could you can just vary the weights, and yeah, you can definitely give a lot more weight to the learned to the real world physics engine.
I have another question, if you don't mind. So how hardware agnostic these models are? So how powerful the hardware should be to for model inference during testing? So should we have like supercomputers or no? So we can like work with like moderately small hardware as well.
Yeah, I think right now they're a little computationally expensive, but when I say a little computationally expensive, I think you might need a GPU, like a 3 GB memory GPU, like on-device GPU, or sometimes I think, or like a hefty CPU core, so like 48 CPU cores. I think probably something in that range. So what we've typically been doing is we have a remote server with some accelerator, and then we like have some type of like interconnection between the two. So like your policy, like your robot can't really have this compute. So like it executes and makes a call to the server that computes stuff and then sends it back. If it's just the action, so let's say like for some of these lower dimensional settings, then you can just run it directly on the device and then it's much faster.
Thank you.
Hi, I'm
Yeah.
Professor Yilun. We meet before in the MIT. I'm Kai Chen. So nice to meet you again. So I have a question concerning your final two example you give in the planning and the multimodality. Especially in the planning one, you give an example about the hierarchical action. It's like you are going to from the LLM and give a very high level task, and then based on this high level text, we give it to the action model, we generated the action, and based on the action, we generated the video, and we try to align the video with the target video, and then we modify the high level text given by the LLM. And you are using the energy model, but this one is quite similar to the previous concept named like the reversed optimization. It's like in the generative model or in the diffusion model, where you give a noisy as an input and you generated something, and you're trying to align this final output with your target by optimizing the noisy. So what is the difference and what's the advantage of your methods? I mean, you can also do this similar reverse optimization to the to this sequential model, like the hierarchical model from the LLM to the action model to the video model, instead of doing the energy-based function. So it's a advantage comes from the computational efficiency, or it's from the accuracy, or is there any other reason for using that?
Well, I guess I'm not sure if I'm familiar with the diffusion stuff, but I think overall, like I guess like this idea of like using optimization to like, so you have a set of constraints, right? And you want to find some way to optimize the constraints. Like this is, I guess this has been around for a long a number of decades. But I guess like overall in this approach, what we want to do is we have this language model, we have this video model, we have this action model, and we essentially want to optimize for a sequence of actions from each of these so that you can satisfy the constraints with respect to the other models, right? And then we're just proposing like a type of optimization procedure to solve that. So I'm not actually sure how the diffusion setting actually applies to this setting, because we're not like actually trying to do some type of diffusion optimization, right? Like we're actually trying to just optimize the sequence of inputs to satisfy this overall objective function.
Okay, thanks. And another question is like, in the VLM and the clip example, you are using the clip like the discriminator in the generated model in order to judge whether the generated text is quite aligned with the image. So would that performance be largely restricted or constrained or limited by the clip model, or yeah?
Yeah, so I guess it was more of a qualitative example, but yeah, so definitely like the particular framework I showed where you have this clip model and language model, like it can't solve a lot of tasks, right? So like if I ask it like what is not in the image or something like this, like clip cannot like actually do that alignment, right? So yeah, it is the case that like it is restricted. So I guess the overall idea is we want to have some type of vision language expert and some language expert, and you want to combine them. I don't think you actually want to probably use clip as your actual final vision language model. But yeah, definitely in that particular framework, it would be limited by clip's performance at being able to interpret the scene.
Okay, thanks. And sorry for the last questions. It's like in all the multimodality case you given, it's like the model must do it's not individually be the model which can only take like the one input. Instead of in the most example you given, it's like it already can take both language and the vision as input, or both action and the language as input. So and then you're trying to align these several different ones together. So in this alliance process, again, the performance would be largely limited by the largest model, like the AIM in this example.
So I don't think that is correct, right? So like actually you could even imagine that if you had a really powerful video model, right? Your LLM could be, so the search would take a long time, right? But your LLM could be an n-gram model for all it cares. And like even if you have an n-gram model, if you can run enough steps of optimization to find something that satisfies the video model, then you can get a reasonable video plan. So I guess when we have in this constraint formulation, right? It's not the strength of your like overall composed system isn't really determined by the biggest model, rather it's determined by like the overall like constraint satisfaction that you're trying to do. So it is the case that like so as a result, like each component of the system, right, is much more complicated. Like it is not like each component of the system does not limit the overall expressivity. It's like the composed, like solving the constraint of satisfying the vision language model, video model, and action model would be much more powerful than any individual component.
Thanks. Thanks for your answer.
Yeah, thanks.
How many energy functions can you combine before you run into problems?
Yeah, I think that in a zero-shot manner, we can probably do like 5 or 6. If we so one thing you can do is when you have these energy functions, you can also train the composition of the energy functions to satisfy your data. And if you do this type of training, we've been able to do 100 or 200 or a couple, yeah, like pretty much as high as we want. But if it's like just zero-shot, like these are very different energy functions trained by different models, then like around 5 or 6, you start hitting these like local minima issues.
Thank you.
Actually, I have one question, Yilun. I saw your fifth generation example. You kind of decompose different part of the face, the hair, the face. How did you set up the learning objective for those energy-based functions so that you can focus on different parts of the face? Yeah. If I missed anything, can you clarify?
Yeah, sorry. I think that portion went by a bit quickly. So in that portion, we just have this overall objective function that we want to discover 4 energy functions so that the sum of the 4 energy functions allows you to recover the original face. And then we restrict it so that each of these energy functions sees a very small latent encoding of the image. So the energy functions themselves learn to capture each component of the face. But like our overall objective is just like decompose the image into 4 separate energy functions that are approximately factorized.
So the constraint actually you want the whole face is represented by like 4 energy functions. So then each part is kind of represent part of the face.
Yeah. So like, the constraint is just all 4 need to represent the entire face, but then because the latent dimension is pretty low, the most effective way to encode this would be to have each of the energy functions capture parts of the face.
Great. Thank you. Who else have questions? If no questions, we thank Dr. Du's seminar again, and we'll keep in touch.
Yeah, great. Thanks so much for having me. Yeah, it was really nice talking with everyone. And yeah, I'd love to chat more if people have any questions also.
Who wants to have more conversation with Dr. Du?
Yeah, or like feel free to send me an email afterwards. Yeah.
Yeah, sure.
Okay, great. Okay, thanks everyone. See you.
Thank you. Bye-bye.